we've looked at two ways of proving things mathematically, which is direct proof and indirect proof. And now we look at a third way, which is useful in some situations. So you've often probably heard about the domino effect, which is if you can imagine a whole bunch of dominoes all lined up together, and you know, even without actually doing this, that if you knock over the starting domino, for example, this domino, then all the dominoes are going to fall over. And it's really the logic behind this that we use in induction. So let's just think about how, if you see all these dominoes, you know for sure that they're going to fall over. So the thing that you know, or that you're going to prove, if you like, is we're going to prove that all the dominoes fall over. So there are two things that you need to know, which will then lead to the conclusion that all the dominoes are going to fall over. You need to know two things. The first thing is that you can knock over the first domino. So our proof is going to start off by saying 1, we can knock over domino 1. Domino 1. So this is really saying domino 1 falls over. So we need a proof of that. And this you know, if you've ever knocked over one domino, you know that it can happen. And then the second thing that you need to know is that if I knock over some domino, let's call it domino k, so for example, if I knock over that domino, then the domino next to it falls over automatically. So domino k plus 1 . So this is really saying if I prove that if domino k falls, then k plus 1 falls. And these are the two things that you know, and as a result, you conclude that all the dominoes fall over. And this is kind of a thought experiment that you can do, which will prove that all the dominoes fall over, even if you don't actually knock them all over. And this is exactly the same reasoning that we use when we do proof by induction. So mathematical induction is a proof technique that uses this idea. So we've got some property that's defined for all integers n. So in our domino example, our property n was that domino n falls over. And we're going to let a be a fixed integer. So in our example, this was going to be 1. And then we suppose that the following two statements are true. So in our case, PA, which was P1, is that domino 1 falls. This is saying we know that we can knock over the first domino. And then the second thing that we have is that if pk is true, then pk plus 1 is true. So in our example, this was if domino k falls, domino k plus 1 falls. So because we know that these two things are true, then we can conclude that for all integers bigger than our starting value, which in our case was 1, we have that our property is true, which in this case was that all, so this tells us that all dominoes fall. So just to summarize, the key behind mathematical induction is you want to prove something for all integers. You want to prove some statement for all integers bigger than some particular a. And you go about this by proving that what is called the base case is true, and then you prove that if the property is true for some integer k, then for pk plus 1 it's also true. So we're going to look at a lot of examples of how to do this, and you'll get the hang of it pretty soon. So whenever you're thinking about this, think about how you would prove that the dominoes fall over. Well, remember, you always have to prove that you can knock over the first domino, and then you have to prove that if you knock over domino k, it's going to make domino k plus 1 fall over. So here's an example using maths rather than dominoes. We want to use induction to show that the sum of I from 1 to n is equal to n plus 1 over 2 for all integers bigger than or equal to 1. So we know that we need a proposition. So we're going to let our proposition be that the sum from I equals 1 to n of I is n plus 1 over 2. So we want to prove that our proposition, which is this thing over here, is true for all integers bigger than or equal to 1. Well, the first thing we need to do is prove that it's true for our base case, or the smallest number. So in this case, since we want n bigger than or equal to 1, our a is equal to 1, if we go back to our definition up here. So the first thing we do is we show that P1 is true. That is, what we want to show is that the sum from I equals 1 to 1 of I is equal to 1, 1 plus 1 over 2. And if you just figure this out, you know that this should be equal to 1. And the way we go about this is we're going to look at the left-hand side, which is this bit over here. And we're going to say, okay, well that means we need to go sum from 1 to 1 of I is equal to 1. That's all we've got. And then we look at the right-hand side, which is that bit over there, and that's equal to 1 times 2 over 2, which is equal to 1. And since our left-hand side is equal to our right-hand side, P1 is true. So what we've really proved here is that we knock over the first domino, that the first domino can fall. Now our next step is we need to show that if pk is true, then pk plus 1 is true. Now pk says that the sum from I equals 1 to k of I is equal to k plus 1 over 2. And we're assuming that this is true, because we're saying if pk1 is true. So we assume that this is true, and now we want to use that information to show that pk plus 1 is true. So let's just check what pk plus 1 is. pk plus 1 is going to be the sum from I equals 1 to k plus 1 of I, and then it's going to be k plus 1, k plus 1 plus 1, which is k plus 2 over 2. And we want to prove that this is true, assuming that pk is true. Well, let's see what we can do. We know that the sum from I equals 1 to k plus 1 of I is really the same as the sum from I equals 1 to k of I plus the very last term that we have over here, which is just k plus 1. And if we carry on from there, we know that this thing is the left-hand side of pk, which we're assuming is true, so we know that in fact this sum is equal to k plus 1 over 2. So we've got k plus 1 all over 2 plus k plus 1. So we're almost there. The next thing we need is to just put everything over a common denominator. So we've got k plus 1. I'm going to multiply this top and bottom by 2. So I've got plus 2k plus 2. And this is all over 2. And now if we simplify this, we've got, let's have a look. Well, we've actually got a common k plus 1. If I'd rather kept that as 2 times k plus 1, I can take out a k plus 1, and then that's going to leave me with a k plus 2 over 2. And that is the right-hand side that we wanted to prove that pk plus 1 was true. So since we've shown that the left-hand side is equal to the right-hand side for pk plus 1, given that pk was true, and so we have that pk plus 1 is true. So finally, combining these two things that we've done, so our first step showing that the base case was true, and our second case showing that if pk is true, then pk plus 1 is true, we can conclude that our Pn is true for any n bigger than our base case. So this is a pretty standard way that proof by induction works, and now we're just going to look at a few more examples. So you'll notice that pretty much every proof we do follows the same method when we're using proof by induction. And in a test or exam you will be told to use in mathematical induction, so you'll know. So the first thing is that you need to have some property P. So sometimes this will be given to you and sometimes you have to construct it. And then you need to do two things. You notice what your base case is, so you want to prove for all integers some bigger than some particular number, and that will be your base case, that number. You show that that case is true, and then you show that assuming that pk is true, then pk plus 1 is true. And this has to be the case for all integers, k bigger than our base case. And in order to do this, you suppose or you assume that pk is true, where k is any particular but arbitrarily chosen integer. And using that information, you show that pk plus 1 is true. All right, let's have a look at another example. So we want to show that the sum of a geometric sequence is r to the n plus 1 minus 1 over r minus 1, where our geometric sequence is r raised to the I, and summing over I goes from 0 to n. So the first thing we need to do is we always need to have a proposition that we're proving. So I'm going to kind of call this step 0, which is define what our property is. So I'm going to say let Pn be the statement that the sum from I equals 0 to n of r to the I is equal to r to the n plus 1 minus 1 over r minus 1. So for the moment, so what this should actually have over here is a 0. And this tells us that our base case is going to be 0. So our step 1 is to prove that P0 is true. That means we want to show that the sum from I equals 0 to 0, because we're doing the case A equals 0, is equal to 0 plus 1 minus 1 over r minus 1. So we're going to have a look at the left-hand side of this. Well, the sum from I equals 0 to 0 of r to the I is equal to r to the 0. And this is equal to 1. And for the right-hand side, we want to have r to the 0 plus 1 minus 1 over r minus 1. And this is going to be equal to, well, r to the 0 is going to be r minus 1 over r minus 1. And now you see why it's important that we have that all real numbers are except 1, because if r is equal to 1, then we'd have, so r equal 1 would give us 0 over 0, and we don't know what that means. But we say, since r is not equal to 1, because we specified that we're not proving this for r is equal to 1, this is just equal to 1. This is just equal to 1. And so we've shown that our left and right hand sides are equal when we're looking at the case n is equal to 0. So P0 is true. The next case that we want to look at, our step 2, is we assume that pk is true, i.e. let's just check, this is the sum from I equals 0 to k of r to the I is equal to r to the k plus 1 minus 1 over r minus 1. So that we've got to work with, and we need to show that pk plus 1 is true, i.e. what we need to show is that this equation is true. So this is going to be an r to the k plus 2. And again, we use a left-hand side and a right-hand side. So we've got a left-hand side, and we use a similar trick. We want to be able to use the pk plus 1. So we need to transform this sum to k plus 1 into a sum that includes just k. And it's always easy to do that. The sum from I equals 0 to k plus 1 of something is equal to the sum from I equals 0 to k of the something plus the k plus 1th term, which in this case would be r to the k plus 1. And now we can substitute in for this sum over here, because we're assuming that pk is true. So we know that this is r to the k plus 1 minus 1 over r minus 1. And then we need to add this term, so that's r to the k plus 1. And now we can just put things over the same denominator again. So this is an r k plus 1 minus 1 plus r minus 1 times r to the k plus 1 all over r minus 1. And what have we got here? Well, let's just multiply these things out. So I've got an r to the k plus 1 minus 1 plus this r times this r to the k plus 1 will give us an r to the k plus 2 minus r to the k plus 1. So these are going to cancel. This whole thing is over r minus 1. And if we just reorganize our numerator, we've got r to the k plus 2 minus 1 over r minus 1. And this is exactly what we wanted to show over here. Whoops, and that should have been a 2 there. So this is equal to the right-hand side of our proposition when k for k plus 1. So this shows that if pk is true, then pk plus 1 is true. And therefore, by induction, our proposition is true for all n greater than or equal to 0. So it's a good idea to work through these examples in detail, and in the next lecture I'm going to give you a few more examples that we work through and also some for you to work through yourselves.